Okay, so let's talk about the lab results that we saw in class today. First of all, we're talking about water. We know that water falls from the sky as precipitation. And when water gets to the ground, it can do one of only two things. That's it. When water hits the ground, it either infiltrates or it runs off. Runoff or running off is just water that stays on the surface. It's going somewhere. It's running off. It's sliding down the hill. Water that infiltrates is going through the process of infiltration. So that begs the question, what does it mean when I say infiltration? Infiltration is the process of water moving into the ground, at least in our context. Water can infiltrate a lot of things, but we're talking about the earth. So we're talking about water that's infiltrating into the ground. So here's how we tested water infiltrating the ground. We had some sand, some gravel, and some clay. And we poured the same amount of water in this tube, and we let it infiltrate into that material. And you saw it would infiltrate. It would go into that material, but not all material is the same. The rates of infiltration are very different when you change the material. You should have seen that the water infiltrated into the gravel almost immediately. As fast as you could pour it in there, it went in. The sand, well, it still went in there pretty quick. So water infiltrates sand pretty easily. What you saw is the situation here. You'll notice the water is taking a long time to infiltrate the clay. It doesn't go into the clay very easily. Now, there is a word for this process, word for this phenomenon. It is called permeability. To be permeable means that it allows water into it easily. Permeability is a description or a measure of how easily water is to go into a different material. The gravel is very permeable. The water gets in there really quick. Sand is pretty permeable. Water goes in there pretty quick. If you ever played at the beach and you're pouring water on the sand at the beach trying to make a sand castle, maybe trying to get like a little moat around it, you know that the water, as soon as you pour it into the sand, it pretty much goes in almost immediately. Clay, however, we would say clay is not very permeable because water doesn't go into it very easily or very quickly. So what happens to water after it infiltrates the ground? Well, gravity still works, and you can see my sand here. All of my water has been pulled to this lowest point. Groundwater that we're going to talk about is typically very deep underground. It's not up here. Our ground typically sets up like this. We've got an area up here at the top, which looks kind of dry. And then we got a point right here where the water starts to collect. This is how most of our ground is set up. These areas in this point has a name. This area on the top is called the zone of aeration. Aeration. In other words, the space in between my sand in here is not filled with water. It is filled with air. And that's why we call it the zone of aeration. On the bottom, where my ground is filled with water, we call that the zone of saturation. And you remember from when we talked about atmospheric moisture, we know to be saturated means that you are full. And that's what we have here. Down here, the ground is full of water. It can't hold anymore. Well, this point right here, this little line where we can see where the sand starts to become saturated is called the water table. The water table is the point underground where the ground is now saturated or full of water. So let's talk about that water table or that point where the ground starts to be saturated. The water table isn't always the same because the ground is not the same everywhere. And if you get more water going into the ground, that water table can rise. If you don't get a lot of water going into the ground, the water table can go down. The material that the ground is made of makes a big difference or makes a big deal as to where the water table is. These two cups here have about the same amount of sand and gravel in them. I also poured the same amount of water in each one. And you'll notice here with the gravel, we still see some gravel on top. This water is colored. You see, there's my water table. It's almost at the top. But here, I poured the same amount of water in my sand, and the water table wound up here. So different materials, even with the same amount of water, are going to have a different water table because different materials hold different amounts of water. That is a term called porous or porosity. To be porous means you have pores, you have open spaces. Porosity is a description or a measure of how much open space do you have. Well, you can see with the gravel, you can look at it and you can actually see the spaces in between each little chunk of rock. There's a lot of space in there. This material is very, very porous. Now, sand is usually described as being pretty porous because sand can hold a lot of water, but we can't see the open spaces in there quite as much. This is just a good visual to show you this is more porous than this. This can hold more water for its size because it has more open space than this right here. Now you'll notice here's my cup of sand. You notice my water table is now up here. That line where the ground starts to be saturated is now higher than it was before. What changed? Well, I poured more water in here. So with more water going into the ground, my water table is going to rise. Now, can water come out of the ground? Think about our water cycle game. There is a way for water to come out of the ground. So if more water is going into the ground than is coming out, the water table is going to go up. If there is less water going into the ground than is coming out, my water table is going to go down. Now, underground, sometimes we have a lot of water. Like in this case here, man, I can see all that water that I have down there trapped in between the rocks and all those open spaces. If you have enough water underground, like it's usable water, like there's a bunch of it down there that you can get to and use for your needs, you have what's called an aquifer. An aquifer is a collection of usable water underground. It's a lot of water underground. You can kind of think about it as an underground lake, but it's not really one big open space. It just means there is a lot of individual open spaces under that ground that can hold a lot of water. That is called an aquifer. So I would make a suggestion that you draw a rough diagram in your notebook to kind of show you the zone of aeration, how it relates to the zone of saturation, and that water table. In addition, you need to understand these big ideas about the water table, and that the water table can change and go up and it can go down based on the amount of precipitation. And the water table is different in different places because the ground is different places, and different places get different amounts of precipitation, which is where that water in the ground comes from in the first place. I want to show you some examples of some places that have really high water tables. First of all, state of Florida. State of Florida, we know is very, very low. It's surrounded by water. It's a peninsula. And it rains a lot in Florida, which means there's a lot of water in the ground in Florida. If you start digging, some places in Florida, you can dig in your backyard and you'll hit water within 5 feet. This is why people in Florida can't have basements, because if you dig down in the ground, you're going to hit water because the water table is so high. And if you have a concrete basement, the water is just going to come in the basement, which is not good. In New Orleans, which we remember, a lot of New Orleans is already below the water line. The water table there is so high that in many places, people can't be buried in the ground when they die, because you dig down and you'll hit water. So instead, people's coffins are interred in these crypts that are built above ground. And there are many examples throughout history, places where cemeteries were at a place where the water table came up a lot and the coffins actually got pumped up out of the ground by the moving water and started to float away. A swamp or a wetland is just a place where the water table has come up all the way to the surface. This is a local wetland. This is the Big Creek Greenway. It rained a lot, and the water table came up so high that now the water table is above the ground. We wait a couple days, and the rain's going to dry up a little bit, and this water is going to take some time to seep in the ground, and the water table will be back below the ground. So why is this groundwater? So why are we spending any time talking about this? Well, groundwater historically was very, very highly sought after because the stuff in the surface water can be unhealthy. And I want you to think about, like in pioneer times, you still have to drink water. If you went to the river, there was a problem because you don't know what's in the river. You could have Farmer Johnson's cow here is peeing in that river. You don't know what kind of chemicals were dumped in the river from a factory. River water, lake water is inherently unsafe to drink, and it can make people sick. In the old days, in medieval times, especially in Europe, people would take their chamber pots, because they didn't have indoor plumbing. They would poop and pee in a pot called a chamber pot, and they would dump it into the street. And they would come along, and then they would let water run through the streets, and it would wash that nastiness away. Well, where does that runoff water wind up? It winds up in the river, which means our rivers in old Europe were especially unsafe to drink. And there was all kinds of historical examples of people getting sick and plagues and diseases that were spread by drinking unhealthy water. This is why in Europe people started to tend to drink ale or beer instead, because it was fermented and it was brewed and it killed all of the harmful bacteria in the water. You don't know what's going in your river water. You would never ever want to take a drink from the cleanest river in the world. So, deep underground though, there's no plants, there's no animals pooping deep underground, there's no bacteria, there's no pollution. So the water down there will not make you sick. Well, you always need clean water. So towns tended to develop around good sources of groundwater because we knew it was clean, it would make you sick. Now the question becomes, how do you get to that clean water that's deep underground? Rivers are easy, they're right there. How do you get to groundwater? Well, that's the concept of a well. A well is simply a man-made access to groundwater because we want to get at that groundwater because we know it's safe to drink and won't make me sick. I have all kinds of old-time examples of, well, these are step wells. One in India where they dug a well deep enough and people just walked down the steps and would get the water and take it out. A lot of cities and towns commonly had a community well that was protected, and people could go to that well and get the clean water that they needed. Now, this is actually one here in Bishop, Georgia, a little town near Athens, and it's still there. People don't use it anymore. Most of these wells have now kind of gone away because we've got modern plumbing and we don't need these wells as much. But you'll still find some around. This is the Pryor Avenue well in Milwaukee, Wisconsin, middle of the city. And people still go there and will get drinking water to this day. There's a public well in the center of a town called Kusadasi, Turkey, big city, a lot of people, a lot of water needed. So they dug this well, the water comes up, and that gives people access to good, clean water. Here's one in Mykonos, Greece, and I would love to know how old this well is. And it was a real simple process. It was just a hole dug in the ground so they hit water, and there was a bucket there, and it was on a rope. And to me, this looked ancient. While I was sitting there, somebody came along and actually got a sample of water from this well. So it's still a way to get good, clean drinking water. This well here in Vietnam, the Bale well, because the ground in that spot is different than the ground in some other spot, different well waters sometimes have different properties and or different taste. This particular well here is sought after because of its composition and its minerals and its taste for cooking a particular noodle dish in this city called Hoi An. And the restaurants in that area will actually send somebody there to collect the well water to use it to make that specific noodle dish. Now, most modern wells, people still use wells, especially out in the country, not too much in the city. They look like this right here. Somebody drilled a pipe deep underground and started sucking the water out of the ground. Houses in the country, you'll see this little house over here beside the main house. And that's not a dog house. That's what I call a well house. The top of the well is protected, and it sucks the water out of the ground and sends it through a pipe to the house. Problem is, when you start drawing water out of the ground, you start drying up the ground. We get this idea of the zone of aeration and the zone of saturation. Your well has to be into the zone of saturation in order to hit water. But what happens is you start drying out the land around your well. And you get this cone-shaped area where the land is dry around your well. That is called a cone of depression, and it can make your well go dry, which is bad news because that's how a lot of people still get their water. They get them from these wells. So you have to drill the well deep enough so that the cone of depression isn't big enough to dry up your well.
Notice this area back here behind me. You can tell by the view it's very, very dry and brown. I'm in Utah. It doesn't rain very much here. It rains very little at all. But if you'll notice here, they're growing corn. And corn is a very thirsty vegetable. It takes a lot of water to grow corn. So the question becomes, how can they grow corn here if it doesn't rain very much? Well, here's your answer. If it's not falling from the sky, they must be getting water from up under the ground. This right here is a good example of a well. It doesn't look like what we think of with a well where you've got a hole in the ground and you crank the bucket down there and scoop up water. This is what most modern wells look like, especially the ones that are found on farms, which is what most groundwater is used for today, and that's in growing crops. There's our pipe, and it goes hundreds of feet down there under the ground, and it brings up the groundwater, and it sends it through these pipes here and sprinkles it on top of our corn, and that allows our corn to grow. Remember that most groundwater use in our country is for growing crops. Now, you don't see a lot of these in Georgia, because in Georgia it does rain enough. You're going to see these more in the middle part of the country where there's a lot of farmland but not as much rain. So they make up for the lack of rain by getting water out of the ground.
Okay, because these wells have a center point and the sprinkle just kind of rotates around that center point where they dug the well to get to the water, a lot of the fields in the west where they have to use well water because they don't get enough rain are circular. Have you ever flown out west, and as you get far enough west, you look out the window of the plane, you start seeing these really green circles, and those are crops that are being grown with well water. Now, underneath the middle part of our United States, we have a huge aquifer called the Ogallala Aquifer, and it's named for a town in Nebraska where it was first discovered and accessed. And what they figured out was, man, there was a lot of usable groundwater down there. They didn't even realize it. In the Dust Bowl time, and you remember the Dust Bowl from U.S. history, it was a time where there wasn't enough rain and farms basically turned to dust. What they didn't realize in the 1920s and 30s during the Dust Bowl was there was actually a lot more water under their feet than they realized. There's this big, huge aquifer called the Ogallala Aquifer, and it is over about 3 or 4 states, and there's a lot of water down there. And that is our most important aquifer in this country, because I want you to think about, what do people in that part of the country do for a living? They farm. They specifically grow corn, and corn is a very thirsty crop. It needs a lot of water. Well, now our corn crops have a little bit of an insurance from those Dust Bowl problems, because we know there's that big, huge aquifer underneath the ground. Some kind of weird facts: if we took all the water out of that aquifer, it would cover all the land area of 50 states in about 1.5 feet of water. That's a lot of water. But if we were to drain it, it would take 6,000 years to refill naturally, because it's in a part of the country that doesn't get a lot of rainfall. Almost 90% of the water that we take out of that aquifer, we use to grow our corn. Now, we got some real serious concerns about that aquifer, and it's a big important one. First of all, we know that wells take water out of the ground. And when wells take water out of the ground, the water table is going to drop if enough water doesn't go back into the ground. And in that middle part of the country, it doesn't rain as much like it does here. So we got all these farmers taking water out of the ground, and the water table drops, and the aquifer is being diminished. Well, you know what these farmers are going to do? They're going to drill their wells even deeper to get at that water that they need to water their crops. This brings up the concept of recharge, discharge, and balance. Recharge is just the aquifer getting water going in. It's being recharged from water from precipitation. Discharge is the water that comes out, whether it's natural or most times we're talking about man-made, wells sucking it out. And the balance is just what it says it is. It's the balance between the two, just like balancing your checkbook. You got money coming in and money coming out. The balance is the net between how much is going in versus how much is going out. A negative balance means the aquifer is going down. You're losing water faster than you can get it back. Some doom and gloom predictions say that by even as close to 2028, we're going to start running out of water in that aquifer to the point where we won't be able to use water like we have been. There's another big concern that's been a big political issue in the past couple presidential
terms. That's the Keystone Pipeline. The Keystone Pipeline is an oil pipeline that was proposed to come from up here in Canada, and it was going to take oil down to the Gulf of Mexico where we turn it into gasoline. Well, it was going to go right through a significant part of the Ogallala Aquifer. And people were upset about that because oil pipelines can sometimes fail. They can leak. And the pipeline was underground. If the water goes into the aquifer, it could render the water dirty. Remember, we like that water underground because it's nice and clean, so we want to keep it clean. So this has gone back and forth between a couple presidential administrations. President Trump green-lighted it and said, go ahead and build it. President Biden then came in and said, no, we're going to stop working on that. So right now, the best proposal is to go around, stay out of the aquifer's way. But obviously that costs more money, and the oil companies don't want to spend the money. Here in Georgia, groundwater is not a big deal for us because it rains a lot, and all that rain winds up in the Chattahoochee River. Chattahoochee River pretty much always has enough water for our needs. Here in Georgia, almost every place in the state of Georgia is close enough to a river that they can go to the river and get their water out of the river. They run it through a water treatment plant, clean it up. So we don't have to dig wells like they do in the West, where they don't have enough precipitation to have a lot of rivers. In the United States, there are a bunch of different aquifers around. And you'll notice here in Atlanta, we're in the white. There is no significant aquifer underneath us. And that's because our ground doesn't hold a lot of water. It's not because we don't get enough rain here. It's just because the type of ground we're at doesn't hold a significant amount of water. But if you look at Florida, to our south, in South Georgia, there is a significant aquifer down there. Where the ground is flatter, generally from this line going this direction towards Florida, and sandier, but still gets a lot of rain, you get a lot more water under the ground in South Georgia and Florida. And it's actually called the Florida Aquifer. Now, nationally, the 87% of our population now get their water from a pipe that was from a water company somewhere, in town or the county. Only about 13% of homes get their water from wells anymore. In 1950, about a third of people still got their water from wells. Most groundwater today is not used for drinking. It's used to water crops. These are the states that take the most water from the ground: California, Texas, and Florida. Florida, because the groundwater is all over the place and it's clean, it's actually easier to get groundwater in Florida than it is to get it from a river because you don't have to go down very deep. Texas and California, both places where they have significant agriculture, but they don't really get enough rain, especially California. California gets very little precipitation. We know that. But once they discovered there was a big aquifer down there that they could get water out of the ground, they started growing crops like crazy in California, even though it doesn't rain much. Now, I have 3 slides here for check for understanding. You should pause the video, go through these, and see, are these things that you have in your notes? There's the second one. And there's the final one.